To begin our lesson on law of sines, we first have to remember the congruence axioms from geometry. Remember that anything that's congruent means that all side lengths, all angle measures of two different shapes are equal to each other. So, the first was the side angle side axiom, which is saying that if we have any two triangles where we had a congruent side, angle, and second side, so the angle was actually in between the two sides, then those two triangles would be congruent, meaning if I know this information on a triangle, there is only one triangle that can exist. The second was angle side angle. So if I have an angle, a side, and a second angle, then what that tells me is that these two triangles are congruent, or if I'm given this piece of information, two angles, the side in between them, that only one triangle can exist with that information. The nice thing about angle side angle is that the third side is given to you, but it's very easily calculable because there's only one value that it can be. We are going to use this information to begin to solve oblique triangles, and according to your notes, an oblique triangle is anything that's not a right triangle. Make sure, though, that you understand that if you have three angles of a triangle, that doesn't mean that the triangles are congruent. Because the angles don't assure congruence, it only assures similarity within the triangles, meaning that these two triangles are related by some scale factor, but they are not necessarily congruent. In order to derive the law of sines, we'll start with any oblique triangle. It can be an acute triangle like the one on the left, or an obtuse triangle like the one on the right. Either way, what we've done is we've taken and drawn an altitude from angle B perpendicular to the opposite side. In the case of the obtuse triangle, we had to extend this particular side, but we drew an altitude. From here, we can take the sine of angle A, and we know that that's equal to opposite over hypotenuse, so that would be h over c. On the obtuse triangle, if I take sine of angle A here, opposite over hypotenuse, it's the same thing. Then I'll do the same thing with angle C, sine of angle C. Opposite is h, hypotenuse here is A. On the obtuse triangle, the opposite of C, now remember I'm looking here at this right triangle, so opposite is h, hypotenuse is A. In both cases, I will solve for h in terms of the other variables. So this becomes, remember I'll multiply by c on both sides, and I will get that h, I'll put this down here, h is equal to c times the sine of A. On the next one, I'll multiply by A on both sides. This becomes h is equal to A times the sine of C. I can do the exact same thing over here on the right-hand side. I get the same information. H is equal to C sine of A. H is equal to A sine of C. The important part is the next part. H is equal to itself. So what I can do is I can set H equal to H, or C times the sine of A equal to A times the sine of C. And then from here I can simply do some rearranging. I can divide by C on both sides. I can divide by A on both sides. And what I end up with is the sine of A over A is equal to the sine of C over C. I can repeat this exercise dropping an altitude from angle A and dropping an altitude from angle C. And when I do that, I will get this same type of ratio with angles A, B, and C with sides A, B, and C. And here's what the full law of sines looks like. Now you will usually see me write it in this manner. Sine of A over A is equal to the sine of B over B, which is equal to the sine of C over C. Anytime that you're looking for either an angle or a side, you can use any two ratios. So here we use A and B, you can use B and C, or you can use A and C. It depends on the information you're given and the information that you're looking for. You can write the law of sines either way. One of the suggestions is that whatever variable you're looking for, keep in the numerator. So if you're looking for side length, put the side lengths in the numerator. If you're looking for an angle, keep the angles in the numerator. It doesn't really matter either way. So pick one that you like and stick with it. Okay, so let's try an example. We have triangle ABC. Angle A is 28 degrees, angle C is 102.6, side C is 25.3. The first thing that you need to do is to sketch this triangle. It doesn't have to be perfect. So this is an example where we can very easily find our third angle. We use the angle sum theorem, 180 minus 28 minus 102.6. Angle B is 49.4 degrees. From here, we can simply use the law of sines. I have angle C and side C, so that's what I'll need to use in each one of my ratios. So the sine of 102.6 over 25.3 is equal to the sine of angle A over side A. At this point, I'm going to cross multiply. So 25.3 times the sine of 28, I will divide that by the sine of 102.6, and I will put the whole thing directly into my calculator. This gives me a value for sine A of 12.171. Then I need to find side B. Usually, I say don't use a calculated value, but in this case you have no choice. So you will again use this ratio of sine C over C. And set that equal to the sine of angle B that we calculated over side B. Again, I will cross multiply. And I get a value for sine B of 19.684. And then, of course, angle B, which was the first thing I defined, was 49.4 degrees. Alright, so next we have a word problem. Kurt is wanting to measure the distance across the Big Muddy River. So if you look at the sketch, that's your distance across the Big Muddy River. He determines that C is 117.2 degrees and that A is 28.8 degrees. And that side B is 75.6. Here we've got an angle-side angle situation. So that's one where we can very easily calculate this distance. First thing that I need to be aware of is, do I have all the information that I need, or do I have to calculate something? I know that I'm going to need to use the ratio sine of A over A. So that would be the sine of 28.8 over A. The question is, do I use sine of C over C, or do I use sine of B over B? Well, if I look, I don't have a value for side C. I don't have a value for angle B. However, angle B is something that I can calculate relatively easily because, again, I can use the angle sum theorem for a triangle. So that's what I'll need to do. And I get a value for angle B of exactly 34 degrees. So now I can complete the law of sines with sine of B over side B. Again, cross multiply. When I do that, I find that A is equal to 65.131. This is a word problem, so I need to write my answer out in a complete sentence. The distance across the Big Muddy River is 65.131 feet. This next problem uses bearings as well as needing to use law of sines. So we've got a lighthouse, and the bearing from the ship was north 52 west. So the lighthouse has to be west of the ship. So here's my ship. There's north, and there's my 52 degrees west. The ship sailed due south, 5.8 kilometers. And now the bearing to that same lighthouse is north 23 degrees west. So there's your 23 degrees. So we need to find the distance between the ship and the lighthouse at each location. That means find this distance, then find this distance. If you look, we've got an oblique triangle. We can pretty easily calculate this angle by taking the supplement of 52 degrees. And from there we can find the last angle, so now I can use law of sines. To make things easier, I will just call the lighthouse angle A, so that this is side A. My starting position will be angle B, so here's side B. My ending position will be angle C, so that's side C. So we will start with sine of A over A. I know this drawing isn't the easiest to see. There's angle A. Side A is the 5.8 kilometers. And I set that equal to sine of B over B. And that is a degree symbol, by the way. Cross multiply, and I get that side B is 9.427 kilometers. I will do the exact same thing, but this time I will need to use sine of C over C. I'll begin with sine of A over A because it's the ratio that I was given. Cross multiply, and I get that side C is 4.674 kilometers. This is a word problem, so I do need to write this as a complete sentence. So I might say, the ship was 4.674 kilometers from the lighthouse at its first location and 9.427 kilometers at its second location.